Okay, let us start. So in my talk today, mostly we'll cover that AIML tools, which is very popular and has been used in our data for art science. And the main concept about the data-driven modeling or inversions. And when we will discuss then from the origin to the state of the art where this application is going on in our domains, we will briefly cover it. Mostly we'll discuss about that very popular algorithms, artificial neural networks. Then what are the limitations of the artificial neural networks, how this Bayesian's philosophy coming into the pictures of neural network optimization. Then there what are the, again, improvements, the ways to train these Bayesian neural networks, and some examples of support vector machines theory and very popular other algorithms like random forest, fuzzy logis. So we'll cover in this topic in my lectures, and tomorrow we will again we'll start and cover rest of the part what this AIML tools has been used. So this is what we talked about, that data-driven inversions. As a geophysicist, we deal with this data model relationship that from the models to data, there is a process called this forward modeling, and the data model relationship in a general, I am writing here as a linear as a non-linears, because depending upon the problems we are viewing, it can be posed as a linears or non-linears. In generally, these are G terms, functions of M, E terms, which is the error, with the deviations between your observations as well as the predicted but computed by the forward theory. But data-driven modeling is coming into the pictures that there are many limitations in our conventional inversions. We have discussed that still even things are going on very smoothly. Still we are facing with, say, non-linearity, uniqueness in the problems. Then there is a complex part of noise which may actually mislead you, that original estimations of your model parameters. So that is a non-unique, and geophysical problems like a potential field, let us say, in gravity, like resistivity, they are coming from the Laplace equations, where by changing or combinations of your model parameters, we are able to produce the same observations almost. And then what will be your optimal of the solutions we want to take for further. So in order to address these things, there are alternative approach. We are not saying that this is the accurate one, the final one, but this is the another way we can deal the inverse problem to solve. So we represent or create some training examples, as I said, that what will be your model parameters, what should be your theoretical computations. So we need to gather it that a lot of this forward response in your training set, and that is a one-time job. So once it is done, then by providing these examples to your AI tool, that can learn the relations between the two domains, between input and the target, which will be coming into the pictures. So when we are training these AI or machine learning models, the part is the noise part, which is actually address how the stability can be addressed, and then the uncertainty. It is one of the critical and the important part in the all solving this type of inverse problems, where solutions is characterized by the many complexities. Then noise is another part where makes the problems sometimes very complicated. The order of the nonlinearity, so many things are coming into the pictures, so that the direct estimations are direct straightforward answer once we are giving, we need to also associate it with what are the uncertainty associated with the model parameter estimation. That is how this Bayesian philosophy or Bayesian inversions is very much popular in our domain of our art sciences. So this is the relations, how this data-driven inversions coming into the pictures. So in the conventional inversions, where we have the models that might be geological models of parameters, and we use this forward theory, which to compute this theoretical response. So D is a function of G to M. This operator is a general one. It can be a linear, highly nonlinear, quasi-linear. That gives you the definitions of your nonlinearity. Then the inverse modeling is actually coming from your data to estimate the model parameters. So I am using this estimation because most of our inversion schemes we are using the statistical inference. So the correct way to find that estimations which actually statistically derived. Now in the optimizations of the neural networks or machine learning models, we have your examples that input and corresponding to the target, and then we train the machine learning models of any types of either ANN, SBM or any types, and try to find that what will be the model parameters here. So mostly we do the supervised type of algorithms where the forward response, what could be the possible scenario of M corresponding to your, say, D is exercised. But this is a very fast in the sense that in many tomography problems, we need to use some of the or part of the information to your subsequent iterations. So in that case, it takes that every time computing this gradient, Hessians, and in the large inversion problems, we need to also face the problem of storage, computing this gradient, the Jacobian matrix, Hessians, and other orders. It takes a significant amount of the time. And in tomography, we need to store that type of information in subsequent iterations. But in neural networks or type of these machine learning algorithms can be used in an intelligent way, who can keep that type of information in your subsequent process. And once it is trained, then directly we can apply to retrieve that estimations of your model parameter. So this is that data-driven concept coming to the pictures. There is inputs, there is a learning methods. We need to train the systems. That training algorithms can be divided in trainings, then validations, and the testing stage. These are the pioneer in their field. So Hinton is the inventor of our backpropagation theory. Bhattnik comes into the statistical support vector machines theory of our. Then the Cohen, he is a developer of our self-organizing map. Zhang, he is developing the NPS, Adaptive Neurophagy Inference System, which is very popular in many computing systems in our art sciences. So AI mostly it is a branch of sciences, in the computer science particularly, where this software and hardware in addition part is there. And the machine learning basically is algorithms which is actually used to train that AI systems in different. The AI journey, it is not a new that the first pioneering papers we already referred that the computing machinery and intelligence by Alan Turing, the mind, that he actually writes some pioneering paper that whether this computer can then think of your own. That gives you one of the challenging on the questions at that times, and then over the times it has started its journey, and then coming into the different algorithms parallelly over this world, and they are trying to establish their superiority over the others. And then second revolutions came in 1986, 70 onwards, that backpropagation theory, because there was a limitations of these neural networks of the computing due to the computing speed, storage, and the slow. There are so many limitations were there. That limitation was again characterized by that type of not very efficient computing systems, which was not available everywhere to test all these type of algorithms. And there's backpropagation theories, although it has been credited to the full formalism by Hinton and the group, but initially this backpropagation theory was tackled a scientist called Ibroz in his PhD thesis, who he was taking that what is beyond the regressions. So in that dissertation work, he first used this backpropagation theory. but he is not that highlighted that time because it was not formally known to everybody its computing power. And then MIT group, this Hinton, and they have published this full descriptions of this theory. It finally came into the paper Nature, and it is one of the fundamental and the groundbreaking research in terms of your AI/ML. In fact, nowadays, this super overwhelming popularity to AI systems and their accuracy mainly credited by this backpropagation theory. So AI and ML, there is a relations that mostly it covers this whole, means AI means it is umbrella where almost all intelligence things are coming into the pictures. But machine learning, we are dealing, they are mostly algorithm part, which actually required to train this AI. And there are a statistical part where we need to estimate the uncertainty, probability distribution functions, etc., to address the relationship as well as the uncertainty associated to that in computing the system for the estimation. And there is a data science coming into the pictures because this type of applications, it is not restricted to only computer science. Now this AI/ML has been a part of your everyday life. You see, when we use this today's mobile phones to every systems where it is AI enabled. Even if you do not need the answer, then also AI is there to help you. And there is a lot of things are enabled, and sometimes we feel that it is too much, and we do not need to think about that. Before thinking your process, they are giving some possible solutions. Okay, so suppose you are trying to read some emails, they are first hand some descriptive, the generative AI, they are actually, further they are explaining, providing a solution. Sometimes it is a true, very useful, sometimes it may be a very misleading and confusing. So that is what the things are. But it is a very interesting development over the years. And now there is no questions about its superiority and the foundational things. And it has been used in the various domains of our data reduction, the dimension reduction to clustering, deep learning, classifications in the different domains. And say after say 1991, when the LSTM comes into the first publications, then deep learning and their subsequent development actually in full flow. I think beyond 2000, there is a lot of publications around that. And this is a very good slide. We can briefly see this AI journey from 1943 to say today's, and there is a development from neural networks, back propagations in 1960s, the Hopfield neural network came, then there is a theory by the Hintons, then all these developments, a GPU, CPU, there is a decision tree, regressions, all things are actually coming in the different. These are the landmark or the paper where we have shown that the time. So coming to that, whatever the machine learning tools has been used, most popular one so far or widely used is the artificial neural network. And there is a lot of advantage of these tools. In addition to the computing, it actually inherited some of the functions of the biological neurons. So in addition to the computing, they can also store they can memorize. That is one of the important things, that when we are solving these tomography problems, we need to keep that some information keep in the storage. But once this neural network is properly trained, and it can memorize, recall the fact, recall the informations in that, and that can be readily used for your subsequent calculations. So in that way, this ENN is very effective to compute some of the steps, computing steps in your inverse problem. And the motivations is credited by the three main facts. One is that it is a universal approximator. So you see there is a complex relationship between the data and the models, and that relationship sometimes it is too complicated that we cannot express that relationship in a analytical forms. So but these neural networks can be trained, and it can learn that the complexity of highest order if you properly provide that examples. Example means we have our input and corresponding to the target. Okay, so data and examples, it is a differently we will be using. So far we have talked about the data means it is observations which is acquired on the Earth's surface. Okay, from the data we try to extract the model parameter. But here we will mostly use these examples because that examples contains the informations of your inputs corresponding to the target. So it is just data sets and which contains the informations, and that will be useful for your all type of supervised type of machine learning algorithm. And it is a nonlinear systems. So nonlinearity is a important part because in the general inverse problems, we see that if your problem is highly nonlinear, then first way to tackle this thing, either you can linearize it or you use some purely nonlinear functions to approximate the forward computation. One way to do that, linearize it, you use these Taylor series expansions, you truncate it some orders, so you make this problem linearize it. But in that case, if it is a very multimodal nonlinear problem, so in that case you may not get that one of the global minima you are seeking for the inverse problem. So nonlinearity it is there. But other way to tackle these things, you use this forward response is a purely nonlinear functions like sigmoid type of functions that will give you that more flexibility to map between the input and the target. So the nonlinearity problems has been naturally addressed with the help of neural networks. Third is that temporal changes. So what is the temporal changes? So you are dealing with different type of data, geospatial data over this Earth. One is that your latitude, longitude versus some Earth observations. It may be that it is time series data of your Earth environmental data sets like temperatures, global warming, then evaporation, say groundwater level change, or evaporation change. So many of our time series data, you will see that their statistical properties like mean, mode, things are being changing with respect to the time. So this means that this type of data is inherently non-stationary, time varying field, and their statistical properties has been changing. So in that case, if the temporal changes are there, it is very difficult to capture the physics of their inherent process. Okay, so in that case, nonlinearity is there, but this time varying field, the non-stationarity is another part. So nonlinearity and non-stationarity is not the same. Nonlinearity means if some phenomena is happening with respect to some variable, whether it is changing linearly or non-linearly. That gives you the definitions of your problems is linear or the non-linear. But in a time series forecasting problems, so let us say that you are developing a AI ML tool for the predictions of some variable. So we need to first develop models, how we synthetically predict from your input to the target domain, and then train the models, apply that one. So in that case, this time varying, how your inputs is changing with respect to the time and how it is affecting your predictions of the target, that is whole essence of our this forecasting problems in your time series. So that is very beautifully handled by this ANN. So this is a multi-layer perceptron models. We'll talk about that. It consists of the basic three layers. One is an input, there is a target, there can be a hidden layer. That hidden layer can be one, two, or multiple. That is why it is called multi-layer perceptron. So perceptron is a single layer, or I think the lowest layer of models, mathematical models first used for understanding this type of computer, how they can be think of. Then these problems comes into the pictures that in a complex problems or the complexity one it is increasing, then the only single hidden layer may not be sufficient to map between the input and the target. Then how this multi-layer concept comes into the pictures, and each layers may contains a many number of the nodes or the neurons. That is also another problem, how to choose that, how to fix that number of the nodes or the neurons in each layer. That is also a problem of our optimizations. So here the variables are there, the number of the layers, and then how many nodes of the neurons each layer contains, because these neurons is the basic information processing element here, which actually acts as a mediator to transform that information for your input to the hidden, then hidden to the hidden number 1 layer, then hidden layer 2, like that, and finally it comes to the output layers. And in output layers, again it will match with that what will be your target, the objective in that, which is what we call this in the supervised type of algorithm. Then these loss functions has been defined, and these loss functions will be improved it by iterative process. Then you see that how this minimization problem has been there, it is equivalent to your optimization problem, what we have talked about, that either you can use for global optimizations, local optimization, hybrid optimizations, or combination of the any of these. So here the information is starting from your inputs layers and then move to your say hidden layers, and then move to output layers computing these cost functions. Then cost function has been minimized it by propagating the error at the output backwardly from your target levels of the output level to the input level. While error is back propagating, by once it is there, at the same time it will allow to change the model parameter. What are the model parameters in your MLP model? Here actually the weighting coefficient of the each neurons to their subsequent connecting neurons. So that is a weight corresponding to the input to the hidden. There can be a weight from hidden to the output, like that. If it is a multi-layers, then number of the weights will be actually increasing, and it will be stored in a matrix format, what we have started about. And in this process, it will start from input to the output, and finally this completes one cycle, or call it iteration. So in many of our problem, we studied that how this cost functions is improving. That is the fact. Second thing is that each neurons, how it functions, because this is the sigmoid of the transfer functions we called here. There can be as many number of the transfer functions. Now it is available in the literatures as well as the softwares. But the basic of the most popular is that sigmoidal type of functions. There are two types of functions. One is the tan sigmoid, and another is the log sigmoid. Log sigmoid takes the value from 0 to 1. Tan sigmoid of the hyperbolic tangents, it takes the value from +1 to the -1. And this is the sigmoidal nature. You see, this is a some of you are physics background, you have seen that there is a hysteresis loop, that how these magnetizations actually takes, that is a similar curve. And look at this picture, you see that this is your x, okay, this is your say y, your predictions. There you will see that when you are applying the input, say this is your say net sum, and it will compute this net will be processed through a function that we call it some sort of transfer function. And this will give you the computing the output of your each of this node of the neuron. Now these functions will compute like that, but the beauty of this nonlinearity comes into the pictures that net sum will passes through a function. That function's response is actually showing here. So when your net sum is false, say like these regions, so your functions will mostly act as a linear function. So whatever your inputs of the net sum is, your target will be the same. Linearly it will outperform it. Then comes into the pictures that when your net sum in these regions, then you see this nonlinearity starts into the picture. Here there is a linear to the saturation zone. So here the change of your this net sums will not proportional to the change of your output. So that gives the flexibility that if your relations between the input to the target is highly nonlinear, so by changing these parameters here, what are the model parameters? One is the W, the network weight corresponding to the each neurons, and second is the bias term. So bias in the neuron, bias is a terms which can be randomized it, and this value will be randomized in every times, and that essentially gives that the flexibility that net sum can be fall in these regions. So these functions can act as a linear, these functions can act as a non-linear. Both the things are there. Usually if you use this as a non-linear functions, so both type of functions is there, but this is added things. And it will help you to map the input to the target. Okay, so this is the things has been there, so I do not go into the details of that the functions of your neurons is inherited to the biological neurons, and there is just inputs and the main processing it is your the soma, where the first part is a summation, second part is your the output that transfer of your functions for your sigmoid type of functions or the any transfer functions. And basically these are the three types of very common transfer functions has been used when this neural network coming into the pictures. So one is the hard limiting. So this type of functions values from 0 to either 0 or the 1. So it is a sometimes of discontinuous problems, particularly in the classification problems. We label it the output as either 0 or the 1. So in that case, this type of function is very effective to map the target. There is a Gaussian function, so it is a one type of radial basis functions. So once in the neural network you use this RBF function, then we call this multi-layer perceptron that is a RBF of the radial basis function. Whereas there is a sigmoid type of functions, it is a some sort of log sigmoid because it is varies from 0 to 1. But some of our problems, our output can be your -1 to the +1. So in that case, it is recommended to use this tan sigmoid to cover the negative part of your function. So this is your sigmoid type of function. So this I already explains that this multi-layer perceptron we have to apply from the inputs, computing this at the target, and the minimization takes into pictures. And this first, the backpropagation start from here. We are applying the input vectors, then initialize the model parameter, because it is also problem which starts with the initialization problem in inverse. We have to first initially guess some of the model parameters, otherwise this computing will not start. So here in neural networks also, in your first iterations, so we have to provide that what is the weight distributions and the bias distribution. That is actually you have to provide it. Otherwise, this fast forward computing will not take place. Then this once this output has been computed here when this output is on there, this is your misfit function. Then misfit function minimization which follows that the same process. We have to compute this gradient, what we call the Jacobian matrix. There is a Hessian double derivative of first derivative of the Jacobian gives you the Hessian. This type of computing is there for the optimize. So the backpropagation is not a optimization in sense that backpropagation is allow you to set up the error, compute this setup to compute this misfit up to this, and once it is there, it will actually allow to minimize this process. But when this minimization process will follow, there this optimization takes in the picture. So gradient, if you see this, if you ask the question, say what is the optimization method, we cannot say this backpropagation is optimization. Backpropagation is a method which allow to set up this this error gradient, and then this how this error will be minimized, that will follow either gradient descent or the Newton's or any other methods or any global optimizations method. Clear? So this is how this backpropagation is mathematically computed, because it requires that defining these layers and their subsequent gradient. You see this is your error surface, and this is your target. This is your part which is computed, predicted by your neural net, and this is the computing that this type of error is partial derivative with respect to the W. W is here actual model parameter of your inputs or the hidden layers, or it is a one Ji here. It is the WJI. It is the weight the model parameters or network weight between the input and the hidden layer, where the WKJ is denoted by the network weight from hidden to the output layer. So this error can be computed, and you see this in order to improve this, we computed this W del change of this W of the network weight corresponding to subscript Kj as well as the Gi. And that is related to that the locals and the summation of these locals at the output, it will be a global error, and we actually minimize this global error as a function of this one. Now, this error minimization problem is associated that it may stuck any of your local minima, because whatever the optimization problem with the difficulty of the optimization problem face, here also you will face the same thing, and there is a improvements in that by the use of your learning rate on the step size, and there is a momentum term. Where in this expression, this is your learning rate, and M is your momentum term. Momentum is it is a constant which is actually gives you some sort of thrust, so that we are hoping that this optimization may get out of the trap of your one of your local minima. Okay, this has been used in your chemistry, like catalyst we use in the chemical reactions to enhance some of your things to move it. So this learning rate and this momentum, this is another two parameters we can actually optimize it, or we can change it during the optimization to speed up the process. So this is the full expressions of your backpropagation theory. I will quickly just give the free tour. There is a computing that from your net, and then computing that response of your each node, and then this we set up the expressions of your hyperbolic tangent functions, and this beta, actually the steepness constants will give you that how this nature of your curves are, and then there is a computations of your the error at the output by combinations of this is your target error, and this is the error. This is the things has been predicted by the neural net, and it uses this iterative chain rule. So partial derivative has been used to find out that the expressions of the network parameters of corresponding to the hidden and corresponding to the between the network parameter with the input to the hidden. So backpropagations, it is a good to compute and fast, but when we are applying for your learning this any machine models, the fact that backpropagation theory is that it is a actually iterative process, and your target is fixed. So network, if you allow say infinite time, so and by you exploring the facility of your neural net or the sigmoid functions, it will finally give you the error very close to say 0. Okay, so but while we are doing, we are very happy with that. This neural network training is very excellent, at least it is optimized, but there is a problem with this it memorize some of the solutions which is exposed to your training data. So once you are very much satisfied, directly you apply this trained model to your new data, and it will provide very excellent results in your predictions when the patterns you have provided in your during the training, if it is the same, then this neural network will give very excellent result. But if the new data is there, that some of the examples of the patterns which is not exposed during this training, neural network may fail adversely. So that in order to address these things, this is a curve, a famous curve by Moody, which shows that where we can stop it, the training, because it happens that if we stop in a correct point, then that ANN may overcome the overfitting issue. So this is the ideal models. We can stop the training here. In order to address this, there are many recommendations are there. One is the early stopping technique. That means if you see that say error of the validations or the testing, it is not uniformly changing with the training data, we can stop. So here you see after this point, this training error is decreasing, but the testing error is increasing. Once this point is reached, then we can say that this overfitting starts from here. We have to be very careful about to stop this trading. Okay, that gives you that this the bias variance dilemma. These are both the things we have to keep into mind when we are training this models. So these are the transfer functions which has been used in our different literatures, that sigmoid, pure lines, hard limiting, softmax. There are as many functions are available. So use of the momentum, you see this, these two terms is very, this is used for effective training, and we can say this, how this learning rate can be chosen. You can choose this learning rate, say in between, say 0 to 1. So if you choose the very high learning rates, let us say, so what will be the difficulty will be that it will actually compute that not in very fine scale. So it may happens that some of your iterations through where you are exploring the model space, if the learning rate is very high, so it will take the less time to reach the final computations, but you may miss some of the points of your global minima. So because if you increase this learning rate, it will actually compute this or test all these things, computing the loss functions at that particular interval. So it will miss the in between. So this is one disadvantage of this one. But if you choose this learning rate very small, it takes more time to step, it takes more time to reach this one. But it is again the choice of our choice up to the interpreter that how they are handling this one. So backpropagation start, and then you see this is a curve where things can be changed. You can monitor that what is your goal. So let us say what is the error in the test data, what is the test in the validation data and the training data, and the performance also can be monitored in the 3 data sets, and at the same time we can monitor that trade-off curves, that how your models are not getting overfitting or no, that can be simultaneously can be evaluated. There is a learning rate. So this is a super self-adaptive backpropagations that shows that this learning rate can be variable in your optimizations. So let us say that you are start with some points, and on seeing this your error surface optimization is very smooth. So there is no complexity is there. You may not miss one of your global minima. So you can increase this learning rate automatically. Okay, next step, and it is saying that this learning rate is actually changing exponentially. So exponentially changing means the error surface is very smooth. You are very sure about that there should not be any global minima which may miss it. So in that case, it will allow to speed up this optimization. Now coming to the pictures of Bayesians, that why it is popular, that so in a neural networks we provide that network parameter to initialize it, network weight and the bias, that is given by you. Okay, but the choice of this network weight and the bias is again sensitive, depend on the optimization problem. So if your network selections are given each very away from your optimal one, so it will take much more time to optimize this neural network training. That is one of the disadvantages in the neural network, the traditional neural network so far we have followed. And second thing is that we train it, we predict it, your uncertainty part, that is computed based on a fixed point. Okay, so the standard deviations in your predictions has been computed at a particular point. It has not used any full expression of a probability or the uncertainty at the different stages it is there. Okay, that is another disadvantage of the conventional neural network. Then this prediction uncertainty. Obviously, it is a very problems, because uncertainty is a critical part. Because when you are predicting some of the predictions which is directly related to the human, like cell and slides, like any health parameters, so that is sensitive dependent upon your predictions and the precision. So when you are providing this predictions value, that should be associated with your uncertainty limit, and that uncertainty limit should be calculated very effectively so that you can address or the challenge any of your prediction, how, or you can defend it. So these are the 3 things actually there. So in order to overcome this, these neural networks can be trained with the help of the Bayes theory. So Bayes theory states that suppose you have a present state of our inference, say this present state of inference or the future state of inference, they have some relationship. So if we say this, we are starting an experiment and we have a knowledge about any state of information about the model parameters, say. So before starting any inference or any inversion scheme, that state of information we call it is a prior state of information. Okay, the use of this prior is immense because you have seen in the inverse problems that if we provide say infinite limit of your model space, it will actually take a significant amount of the time to explore this each of these model space point, because each of your point is actually your possible solution. But if you provide that some of the prior information, okay, so let us say density of your say crust, density of your igneous rock. If we have the idea, then we can limit that range. So once this limit this range, which actually gives you that search space is very small, so that way your computation time will be less and your solution will be more realistic, because finally whatever statistically you provided, the geologists must agree with on that what is the particular solution, because they will go for engineers for drilling. Finally, this challenge is that whatever the earth property we are estimating from your observations, finally the call is the exploration part, where they will call the drillers and directly they will drill it and see that how your estimation is reliable to our Earth's models. So there things will be challenged. So a lot of uncertainty is there from your selection of your input to the heading to the target and the relationship. So we are assuming this relation between input to the target is non-linear, but that may be linear at some time. So, and there may be other order of the non-linearity that all comes into the. So Bayesian's actually the cost functions here is a function of W. It is actually divided into the two parts. One is the part we call it is a data complexity that is dominated by the error in your data can be, and the second part is the smoothness of your model. So this smoothness is controlled by this type of total complexity is controlled by the two parameters we call it is hyperparameter. One is your mu, another is the lambda. So mu is your inverse variance of the noise present in the data, whereas this lambda is your parameters we call it sometimes it has been used as a Lagrangian constant, which actually gives you the freedom that whether you are giving weightage towards your misfit, data misfit part, which is controlled by the deviations between the observed versus predictions, or we see that whether our model is smooth one. Okay, so because we have to see in your some of your problem, we have to first assume or hypothesize that how our Earth model is, whether it is very complex or it is very simple. Because things are that we have to guess the initial guess. So that gives you the complexity of your model parameters, and complexity also again given by the how many number of the parameters you are going to estimate it from the inverse problem. That is how this complex problem is. So here this by changing this mu and the lambda is your hyperparameter, where this mu and the lambda finally provide you that suitable optimizations. Again it will actually change that it is associated to the network weight and the network bias. So here this network weight and the bias is your model parameters, whereas this lambda and the mu it is a hyperparameter, which actually again control this network parameter. So here you will see that this posterior distributions of the network weight, say W, provided the S. S is your example set. So S contains the information about the input and the target, and W is your network weight. So we have our likelihood, how close your predictions to your target, that gives you the misfit, and here we are providing its likelihood, that is the negative of your logarithmic expressions of your cost functions, which gives you the likelihood function. So the sense we understand that we are minimizing that error or the cost functions in your say inverse problems. So essentially we are maximizing the likelihood between your predictions theoretically with your observation. So here essentially in order to provide the maximum posterior distributions about the model parameters say W here, we need to control these two things. One is the likelihood, second is the prior state of information. If you see this expressions here, prior is a function of W. So here it is a state of information which is not using the S set. S set is a information where we have the solution, okay, about the data model relationship. But here it is not using. So the prior state of information means we do not have any knowledge about the things about that. What is the state of information before starting anything? Blindly we can have. And that type of information can be used as either you can use a flat prior, you have a broad spectrum, so all frequency informations are there, or you have the Gaussian one. Again, it is a dilemma between the two, whether you go for flat or it is a things are. But finally, the Bayesians will give you that if you have the prior state of information and this likelihood from this data, we can re-estimate the posterior state of information. So every computation is using this Bayesian concept in every step in the neural network. And finally, it provides that computing this all associated constant and finally predict it. So all these details is provided in the slide. I think there is an excellent book by Bishop where these all derivations are there. And you see, we will directly go to there are two ways these Bayesians can be computed. One is that evidence maximization method, another is the hybrid Monte Carlo. So this hybrid Monte Carlo is a purely say some sort of stochastic optimization method, and evidence maximization, it is not the stochastic, but it uses that some approximations of our gradients informations in this computations. And here in the evidence maximizations, so finally you have the parameters say that the probability is your P here, lambda and mu is the hyperparameter here, S is your data set which contains the informations, and here capital P is your probability again, S is your data sets, lambda and the mu. So these terms actually your likelihood, but in evidence maximization, it is actually evidence. So we are maximizing this term. That means we are evidence that what type of representation coming out to that maximum posterior. So this way, scaling is another part because it is related to the physics of the problem. So sometimes it is intractable to estimate it, but to some extent or some sampling methods we may ignore the denominator part. So the maximizing this evidence will give you the maximize the posterior information. So these evidence maximizations allow you that how our hyperparameter also has been estimated by the maximizing the posterior. We call it a posteriori distributions of your model parameter. And there is a part where this lambda and the mu has been actually re-estimated by these eigenvalues and eigenvector solutions to have numerically stables. So there is a two-step process. One is once this network is computed, Bayesian framework has been set up, compute this likelihood another. Then using this maximization method, we find out that hyperparameter, we also maximize it, that the maximum a posterior distribution of about the model parameter, and using that W, say WMP, maximum a posteriori, finally we able to compute that what will be the target. So other way these computations can be done, it is a hybrid Monte Carlo. So hybrid Monte Carlo, it is a Monte Carlo type of techniques, but additional thing is that the gradient informations of the things has been used it. Pure Monte Carlo forms is purely probabilistic. It requires that exhaustive search. So what the exhaustive search is? Here also your cost function is a function of the W and the bias term, and it is sampling the whole model space, and it obeys that Markov chains, Monte Carlo algorithms, where it obeys these three basic properties, that irreversibility is one of the fact, and it is a random microscopic reversibility, so it can move from one step to the next step or any other step that does not takes that information about the previous step. So that is how some of the properties are there. And for computing these things, essentially, we will have the leapfrog process. The leapfrog process is states that once your cost functions has been defined, then this type of functions has been expressed in a Hamiltonian dynamics. So this is a statistical mechanical concept where your energy functions consist of your potential energy and the kinetic energy. And this momentum, say Q is your positions here, P is your momentum here. By defining these things, the Hamiltonian energy we can express in your state-based models and solve these problems, and by the process called this leapfrog, where a series of chain has been constituted, and each of your chain that the frog moves, so it takes that first half step and then full step and then half step. In this way, it will move in the model space and explore the whole energy distributions to find out or to gather which one are the model parameters here has been optimal for your final expressions. So if you go back here, in the Monte Carlo methods, we actually sample that process to gather this WM. So it is a sample. It is a sample which is actually obtained from an exhaustive search. Okay, so I'm coming to that part where so coming to the part with this ANN, we can actually sample this model space, and you see these comparisons that how the synthetic curves have been predicted. You see where your sampling has been very dense, there this Bayesian neural network could able to predict that underlying functions which you want to predict it, and in addition it provides the uncertainty limit. This uncertainty computations is not based on the point estimations, it has been obtained from the full posterior probability distribution or the full covariance matrix at the target vector. Okay, and if you see, look at this, there is no data point, and so the predictions is not very confirmed, so there is a deviation from the true one, but still it can able to emulate some patterns of this one. And if we model, if you sample this whole space more uniformly, there will be more control to emulate the underlying function. This is one of the examples of the first three is actually based on your evidence-based maximizations, which has been used for a BNN. The fourth one is your that sampling. What we have that your underlying functions. So it has actually used this hybrid Monte Carlo with these leapfrog optimizations, where the thousands of probable samples has been assumed, and it explored this model space, and you see where this data sample is highly dense, there this HMC could able to approximate the underlying function beautifully. And once you are away from your sampling, then you see there is a deviation from your observations, but this will give you some guidance about that, how our predictions is close to the true one. Okay, so this is another popular algorithm is your support vector machines. It has been proposed by Vapnik, the statistical inference, and their optimization is not similar to the optimizations we have talked about. And you see this, it has been popular, and it has been first defined for the linear problems, classification problems, and now it has been used for your classification as well as the regressions, where we can observe that there is a problem of classifications where we need to classify the different types of your data. Now, what way we can tackle it? We first plot it in a 1D, 2D, 3D, and see how many data can be easily separated by visual loop. But in many problems, we see that in our art science problems, we have the given data, say well log, and if you plot it, you see that there will be a complete overlap of your sum of your data point. That sum of your features is related to some type of rock type or facies or any types of your problems you want to solve it. So how we can differentiate it that, okay, this type of data belongs to some type of rock or that. So there is a complete overlapping of your things. So we cannot separate each of these points. So this, like neural networks, it handles this nonlinearity the other way. Support vectors is a machine which actually first transform these high dimensional things to a lower dimensional to have the better resolving things and then do the job. Okay. So this is the literature we have given that it solves the basic equations of the cost functions. The difference is that instead of sigmoid functions, it uses these kernel functions and it is controlled by the support vectors, which actually essentially useful to classify that particular type of job, whether it is a classification or the regression. And in solving this optimization problem, some of the vectors which are actually comes out to be a 0, some are non-zero. So some of the vectors which are actually comes to a non-zero, that effectively useful for your classification scheme. So in that sense, we call them, they are the supporting the classifications or the support vectors, and the other things are there, but they will not contribute in the classifications. So this is the basic theory where the support vectors is there. There are different types of functions has been used, of kernel functions, and that is what we have talked about, that the original data, how it is converted to a lower dimensions, and see this how it can be visualized in a better way for your distinct classification. Okay, so this is one thing is left, just we will finish it. So decision tree is it is a very popular machine learning algorithms where versatility is there. It is a very simple and it is a basic block of your random forest models, and there is a base node, a root node, there is a leaf node, and this bifurcation is start from the top to the different level, and how or where we can step it. There is a Gini function is there, which is impurity functions. So this will give you some subject cross check that how this data has been clustered it or classified it in the different levels. And once this Gini is 0, so there is no divisions of your further parent leaf node. That way it will start. So here this optimization is actually controlled by that at what level we want should go, because if you go in the deep, then what will happen? There is a chances of our overfitting and underfitting problem. Okay, random forest is the things which is popular. It is the block where the basic block is your decision tree, and it is actually consists of many decision tree, and each of the decision tree functions, and it is a randomized decision tree because this feature has been controlled by the subset of your each decision tree, and it gives you the freedom to have the more generalized solutions. And this is a very popular things, and where the feature vectors can be used to say that how this decision can be decision can be made from your different level. And finally, this random forest inference will be based on the voting of your as many number of decision tree in your whole algorithm to give you that the more generalized solutions about that any type of prediction. Okay, fuzzy logic is another tool which is actually similar to your neural networks. Only thing is that it is based on the set theory, where this instead of sigmoid functions, it uses that membership function, and membership function acts as your nonlinearity, and there is the layer, say layer 1, 2, 3, 4 like that, and the information will process from input to the target, and the functions, it is a first propagation is based on your forward computations. Then once it is a trend, then gradient descent has been used, and this process will help you to optimize all the other parameters associated in the computation. Thank you.